Hello friends, welcome to UGC PG Pathshala. I am Dr. Lubna Siddiqui, Assistant Professor, Department of Geography, Jamia Millia Islamia, New Delhi. Today I am going to discuss about the module Transformation of Data for Geographical Analysis, which comes under the paper Quantitative Techniques in Geography. Increasing magnitude and dimensions of data availability due to development of information technology in the modern times, there are many issues pertaining to arriving at a level of scientific explanations of hidden geographical facts. Availability of a large amount of multi-dimensional data of real-world situation sometimes creates confusion and incorrect information to draw the facts from collected data. Without proper knowledge of data handling for inferences of facts, the selection of attributes and their uses may lead to a wrong direction in the geographical analysis. Sometimes, uses of selected attributes, variables become wrong if we do not have knowledge of their proper forms for more effective analysis. So, the transformation of these variables makes them usable for finding the appropriate results in understanding their characteristic features in geographic frame. In such steps of procedural analysis of geographic phenomena, transformation of data set is an important step to develop understanding of the quantitative procedure of data transformation and its uses. When information or data about various phenomena, geographical or otherwise, is converted into different forms, it is called data transformation. It is generally done to enhance the information content and also to make it possible for meaningful representation and analysis. Data transformation is also sometimes necessary to make the data of various attributes of different units dimensionless for the purpose of their comparison and aggregation. Now, scales of measurement. Information including dimension of any phenomenon can be expressed through 4 different levels or scales of measurement. In increasing order of measurement in respect of information content, they include nominal, ordinal, interval and ratio. Nominal, which is the initial form of measurement without any numerical value, gives information about various phenomena in terms of name, category, class, etc., that is soil types, vegetation types, rock categories, settlement types, land use categories, etc. Of course, quantitative statements about information are quite significant in scientific analysis, but such statements are informative only and they do not have the logical clues to reach to the reality. Say for example, there are 2 statements given below. One is qualitatively informative and another is numerically data dependent. Number 1. Cherrapunji areas has extremely high annual rainfall. Number 2. Cherrapunji area receives 11,000 mm of average annual rainfall. What do you understand and perceive about the magnitude of annual rainfall precipitated at Cherrapunji? In these 2 statements, first is purely based on perception without accurate information about the amount of rainfall. If the same statement is stated in Rajasthan, a person would perceive meaning of extremely high rainfall to be 2000 to 3000 mm because extremely high rainfall in Rajasthan does not go beyond 1500 mm annually. But the perception of the same statement is different in Cherrapunji. On the other hand, second statement provides accurate picture of annual rainfall due to its numerical form. Quantitative data used, therefore, for scientific explanation provide the correct and accurate information for understanding the facts. Hence, nominal dimension of data or information, that is qualitative, is used for elementary search to make background material for fact finding. When the information about any phenomenon or attribute is expressed in some quantitative form in respect of relative importance or magnitude, rank, or quantitative order, it is called ordinal scale of measurement. Although it is considered superior to nominal scale of measurement, it cannot give absolute difference of value between the ranks or orders. No doubt, ordinal measurement is better than nominal. However, it does not distinguish the accuracy of facts in a given data series because it counts term interval in a series same as rank order and does not have value interval same in the distribution. For example, median, that is measure of central tendency, is calculated by using rank or order, that is descending or ascending of the values of observation of a series. It is due to ordered arrangement of data. Interval scale of measurement of phenomena is purely quantitative. It considers the individual value of each observation in a series. Exact interval between values in a series is the main consideration in this measurement. Hence, when the information about a phenomena is given in terms of some absolute value or magnitude, it is called interval scale of measurement. Ratio scale is more comparative and provides good ground for geographical analysis. The quantitative information about some phenomena which can be meaningfully converted into ratio is called ratio scale of measurement. The basic difference between interval and ratio scales of measurement is that the interval scale does not have absolute 0 and ratio scale has absolute 0. Hence, a good example of interval scale of data is the temperature measured in degree Fahrenheit or degree Celsius without absolute 0. This type of data cannot be converted into meaningful ratio data because 0 degree Celsius cannot be considered no temperature or 20 degree Celsius temperature cannot be said to be 2 times better than 100 degree Celsius temperature. But distance, weight, area, production, etc. are examples of ratio scale of measurement because all these have an absolute 0 and they all can be converted into meaningful ratio values. Now, data transformation techniques. The data transformation basically involves conversion from nominal to ordinal, interval and ratio scales of measurement, and conversion of numerical information given in interval and ratio scales of measurement into various other forms of interval and ratio data for meaningful representation and analysis. Now, data transformation from nominal scale to ordinal and interval ratio scales. Let us first see how the information or data in nominal scale of measurement, whether point, line or polygon data, can be converted into ordinal, interval and ratio scales of measurement. For this purpose, settlements in respect of village and town are considered as nominal scale of measurement. When among the settlements in an area, the towns are ordered or ranked from top to bottom with respect to their population size, area or health facility, etc. It is called conversion from nominal to ordinal scale of measurement. If the categorization of these ranked towns is done with respect to absolute population size or area, it is called transformation from ordinal to interval scale of measurement. But when the absolute data, that is population size, about the categorized towns can be meaningfully converted into ratio in terms of how many times the first order town is larger than the second order one, the second order town than the third order, and so on. It is called conversion from interval into ratio scale of measurement. In order to illustrate the above, let us take an example relating to data about settlements as given below. Table 1 shows capital towns of the states of Northeast India and their population according to 2001 census. Categorization of settlements based on functional character, mainly into village and town, is called nominal scale of measurement. Accordingly, grouping of all settlements of Northeast India into villages and towns constitute nominal data. Similarly, a list of capital towns of Northeast India, that is Itanagar, Dispur, that is Guwahati, Imphal, Shillong, Aizawl, Kohima and Agartala is also nominal data. When the population size of these capital towns in relative term, that is rank, is given, it is called ordinal data. In fact, it is obvious from the second column of table 1 that Guwahati is first ranked city and Agartala is second ranked city in the northeast, but we do not know the exact population of these towns. If population size of these towns is added in the data series and used for population analysis, it is called interval scale. Data used in proportionate form is called ratio scale. It links the proportionate strength of the attributes values. Present discussion gives a concept of transformation of data and its correct form to be used in fact finding. However, there are many ways of data transformation which can be used as per the requirement so as to make explanation of facts more accurate and sound. However, we would describe three most familiar and useful methods of data transformation. Number A, non-linear to linear form of data series. In fact, a time series data of an attribute may have more fluctuation than its smooth change over time. It means there may be extremes in values of observation in a distribution. There may be many causes behind it. In order to find the reasons of fluctuation and fast change in a data series, the nature of its change may be described suitably by using linear transformation. In the case of trend of population growth of towns for a longer period of time, it varies from a few thousands in the case of small towns to several millions in the case of large cities in a country or a large state. In order to show such variation of population growth and its trends, if it is not linear, it cannot be transformed into linear scale through some appropriate mathematical conversion technique. Example 1. To show the trend of population change in Assam during the period of 20th century. In order to illustrate the above example, a set of population data of Assam for the period 1901 to 2011 is considered. Table 2 shows the trend of population in Assam during 1901 to 2011. As the population of Assam experienced rapid increase from as low as 3.29 million in 1901 to 31.21 million in 2011, it witnesses a non-linear exponential trend. It exhibits two linear trends, first one during 1901 to 1951 and second one during 1951 to 2011. In fact, the growth of population has been more rapid during the later period, that is 1951 to 2011. This is visible in the line graph showing trend of population growth based on actual data as shown in figure 1. However, through the logarithmic conversion of the population data, the trend line is transformed into linear one as shown in figure 2. Since time is sealed as unitary and population as variable, the linear form of increase in actual population size is P1 is equal to P0 plus R into P0 into T is equal to P0 into 1 plus R into T, where P1 denotes population of the current area, P0 is population of the base year, R is rate of population increase, and T shows time. In fact, this form does not fit in the general trend of population increase. A semi-log transformation is used to make it linear. The form of the transformation in this case becomes somewhat more appropriate with the following equation. P1 is equal to P0 into 1 plus R into T. Its logarithmic form can be expressed as follows. Log P1 is equal to log P0 plus T log into 1 plus R. In this form, log P1 is the function of T. Note that T follows simple scale and population in log transformed form as shown in figure 2. Figure 1 shows population increase in Assam during 1901 to 2011, whereas figure 2 shows linear trend of log transformed population statistics, that is time series data at x-axis are in simple scale and y-axis shows log population. Now B, transformation from skewed to normal distribution. Distribution of many attributes like land holding size, income, town population, population density distribution, etc. presents a skewed distribution, and sometimes it becomes difficult to represent such data with extreme values in histogram and frequency curve. In view of this, there is the need of data transformation for normalizing skewed data distribution. For more clarity in the concept, two examples, one from distribution of land holding size and another from distribution of population density of the districts of Assam have been considered. Example 1. To show the frequency distribution of land holding size in Assam and its normalized distribution using power function. For this exercise, land holding size data were collected from agriculture census for the state of Assam. As per standard classification of land holding size, the total number of landholders has been classified into 10 categories as given in table 3. Table 3 shows distribution of land in Assam during 2010 and 2011. Here a data set pertaining to distribution of land holding size in Assam as per table 3 is considered to study the nature of distribution of land. The representation of actual data of land as expected presents a highly uneven distribution with concentration of frequency towards very small sizes, that is less than 2.0 hectare. A few landholders have large size of land holdings. Such concavity in frequency distribution shows unevenness and skewness in it as shown in figure 3. If this distribution is transformed into a half value of power function, that is square root power of land holding sizes, the frequency curve becomes more flat with less degree of skewness as shown in figure 4. Figure 3 shows distribution of land holding size in Assam during 2010-2011 and it is based on data collected from office, whereas figure 4 shows distribution of land holding size in Assam during 2010 and 2011 and it is based on a square root transform data. Now example 2. Now let us see how to group a set of individual data of district level population density, that is persons per square kilometer of Assam as per 2011 census data in the form of a frequency distribution and represent the same in the form of a histogram. Population density, that is persons per square kilometer for 27 districts of Assam in 2011 are 280, 1171, 553, 632, 618, 711, 365, 457, 213, 347, 393, 431, 383, 302, 93, 44, 459, 673, 497, 425, 244, 436, 2010, 763, 475, 491 and 497. The frequency distribution of number of districts under each of uniform population density range of 100 beginning from 0 to 100 to 2000 to 2100, and the resultant histogram are as follows as shown in table 4 and figure 5. Table 4 shows the distribution of population density among the districts of Assam in 2011, while figure 5 shows population density pattern in Assam according to 2011. It is observed that a large number of classes, that is 12 classes, do not have any observation, that is no frequency, and accordingly the histogram appears to be almost discrete and less representative. In view of this problem, logarithmic conversion of individual data of population density are done, and grouping to make a frequency distribution of population density is made by taking ideal class interval of 0.2 as shown in table 5. This transformation has made the frequency distribution, that is with only one zero frequency class of population density, more meaningful and better representative as shown in figure 6. Table 5 shows the distribution of population density, that is log converted, among the districts of Assam in 2011. Figure 6 shows log transformed population density in Assam in 2011. Now see transformation for creation of dimensionless, that is free scale data. Transformation of data pertaining to different attributes having varying units of measurement, for example, literacy rate in percentage, road density in kilometer or square kilometer, life expectancy in year, income in money value, and so on, can be done by applying different statistical techniques. Among different techniques, Z transformation and simple transformation index are quite useful. These two simple techniques not only make the data dimensionless, but also give a measure of the relative magnitude of every value in comparison to the mean value, that is representative of central tendency. This transformation finally helps in data aggregation for computation of composite score. The following are examples to understand procedure and utility of these techniques. Example 1, Z transformation to make dimensionless data series. It is to note that in traditional mapping techniques, superimpositions of maps of different attributes are made to understand their composite picture. Statistically, the attributes are converted into standardized scores, that is called free of scale, because the mean, that is central value, and SD, that is dispersion of distribution, becomes 0 and unity respectively after Z transformation, and pattern of distribution remains unchanged because Z is equal to x minus x bar into SD. For making data dimensionless, a data set of literacy rate, hospital beds, and road density for six districts of Assam for the year 2011 are taken as shown in table 6. Table 6 shows socioeconomic data about few attributes for selected districts of Assam in 2011. By calculating the Z value for each attribute and district, the original values become dimensionless as shown in table 7. These Z values are also indicative of the deviation of the attribute value about the mean, that is in both positive and negative terms, in respect of number of times of standard deviation value. The Z values can be 0 when both the observed value of an attribute and its mean value are same. It can be negative when attribute value is smaller than mean value, and it can positive when attribute value is larger than the mean value. Hence, aggregation of these Z values is possible, and it gives relative cumulative magnitude of all the attributes. Table 7 shows Z transformed values of each observation of the above data of table 6. As mean and SD of transformed series are 0 and unity respectively for each distribution, now the standard scores of attributes are comparable and their magnitudes are aggregated to show composite index of distribution. The table 7 containing district-wise composite index of socio-economic level shows that the literacy rate and bed density in hospitals have the highest scores in Kamrup metro district, but it is less developed in its socio-economic level. Example 2, ratio transformation method. It considers only mean unity base of transformation of the values of observation in data series. The value of individual observation divided by the mean of series is the procedure through which ratio of individual values are calculated. For instance, the same data of socioeconomic attributes given in table 6 are transformed to get dimensionless ratio transformed values. Emerging pattern of these transformed attributes are different from Z transformed scores. Kokrajhar district stands first in hospital facilities and Nagaon for road density. It is due to different bases of transformation. Z transformation is mean and SD free scaling, while ratio transformation is only mean unity based to make data dimensionless. Transformation of each individual value can also be done by dividing the same by the mean value as shown in table 8. It makes the data unitless, and this value is also indicative of the extent of the attribute value, that is small or large in comparison to the corresponding mean value. Such value can be 1 in the case of equal observed value of an attribute with its mean, less than 1 in the case of a smaller attribute value in comparison to the mean value, and more than 1 in the case of higher attribute value in comparison to the mean value. The aggregation of such values also finally gives relative cumulative magnitude of all the attributes. Table 8 shows data transformation through ratio transformation data of table 6. It is to note, to get composite index for each district, all the columns are to be added. Now, summary. It is thus clear from the above discussion that the data about various attributes or phenomena can be found in different forms with different levels of measurement. Such data of different forms, that is like non-linear, exponential, skewed, etc., can be converted into linear, normal, etc. forms according to our need and convenience through statistical techniques like logarithmic, square root and square conversions. Besides, for aggregation of data about various attributes with different units of measurement, data conversion can be done through Z transformation and simple transformation quotient. I hope you have understood the concept of transformation of data for geographical analysis. See you next time Thank you.